Alright, let's see if I can help you with this review. I have taken Skill 6 and split it up into 3 parts. So this first part is an emphasis on exponential functions and logarithmic functions and properties of their graphs. So for an exponential function, if it's asking you for the domain, remember the domain is a set of x values for which the function is well defined. For every input you want exactly one output if it's a function, and for any exponential function the domain is all real numbers. So even if there's some kind of a transformation, up, down, left, right, a reflection, it is going to, or a stretch or a shrink, the domain of an exponential function is always going to be all real numbers. Alright, so for the range, you do have to consider the graph. The range is a set of y values. Transformations will change our answer. Here we have this 2/3 is less than 1, so our base is smaller than 1. It's a decreasing function. A quick sketch of the graph looks like this, where the y-intercept is 1. At y-intercept is 1. The coordinates of that point is 0, 1. The x-axis is a horizontal asymptote. Remember, asymptotes are lines or curves that your graph gets closer and closer and closer to. So the equation for the x-axis, or the equation for this horizontal asymptote, is y equals 0. So our graph lies entirely above this line. So remember that the range is a description of the collection of all of the points on the graph, their y-coordinate. So there's one thing that all of these y-coordinates have in common: they're all positive values. None of them are 0, none of them are negative. So the range is the set of positive real numbers. Now that will not always be true. You may have an exponential function that this horizontal asymptote could be lifted up. Say maybe it's lifted up 2 units. The whole graph lifts up. So then that 2 is going to come down here and be 2 to the infinity. Or maybe you have some kind of a reflection across the x-axis where it's the range would be negative infinity up to 0. So whereas the domain of any exponential, no matter what transformation you have on it, it's always going to be all real numbers. You do have to stop and look at the specific function at hand to determine the range. This was just a basic exponential function with a horizontal asymptote, y equals 0, so the range is 0 to infinity. The asymptote, well, we just got done using that asymptote to determine the range. There is no vertical asymptote, so there's no vertical asymptote, but there is a horizontal asymptote, and it's the line y equals 0. You don't want to just put 0. It has to be an equation. It says the equation of the asymptote, and that equation is y equals 0. Alright. The x-intercept. For any function, to find the x-intercept, you let y equal 0. Now, we have 2 approaches to this. We can think of what the graph looks like and immediately answer this just on our knowledge of the graph, or we can try and look at it algebraically. So let's start with algebraically, then we'll confirm it with the graph, with the picture. To find an x-intercept, you let y equal 0. Now, remember that this function notation, if you go back old school, back to Algebra 1 and part of Algebra 2, you just used to call this the y value, not f of x. So if we let that left-hand side equal 0, we are a little bit puzzled, okay? Because there is there does not exist an exponent such that if I take 2/3, raise that value, that you get 0. I can let this exponent x get very, very large, and this number will be a decimal number that's really close to 0, but it'll never be 0. All right. Suppose you didn't recognize that. If you were trying to solve this, you need the inverse of an exponent. Well, that's a logarithm. If you take the log of the left-hand side, then you have to take the log of a right-hand side. So now, hopefully, you recognize that you can't take the log of 0, that this is undefined. Okay? So what our basic conclusion is there is no solution to this equation. And since there's no solution, there's no x value that has a corresponding y value of 0, there is no x-intercept. This graph does not cross the x-axis. Well, we knew that. We knew that a sketch of this decreasing function, that it came down like this, and that the horizontal asymptote was the x-axis. And we knew that this gets closer and closer and closer but never touches the x-axis. If it never touches the x-axis, it can't intercept the x-axis. So again, whether you think of it algebraically or by picturing the graph, there's no way that this graph crosses the x-axis. For the y-intercept, given any function, you let x equal 0. Okay, so remember that we're saying that this f, we can just go back to old school and call that a y-coordinate, a y value, and we've got y is equal to 2/3 raised to the x power, but this time x is 0. Well, by definition, by properties of exponents, a base raised to the 0 power is equal to 1. Alright, so my y-intercept is 1, and some people prefer to write it as coordinates. If you're going to plot, if you were graphing this and you know it's a decreasing function, then you know that it's intercepting this y-axis, that the coordinates of this point is 0, 1. Alright. The end behavior. Again, now here we can try and approach it algebraically, or we can try and approach it graphically. I would think that approaching it graphically would be easiest, but let's say that we were trying to approach it algebraically. If x is approaching negative infinity, that means that this input into this function is some really, really small value. It's negative, and it's really, really, really small. You know, much smaller than negative 10,000. Okay, but suppose we have some negative value here. All right, so let's just not be specific and just say, hey, what if this is a negative number? Very negative, like negative 1 billion, negative 1 trillion. Okay, then this exponent is negative, and it's, like I say, a really, really large in a negative sense number, negative billion, negative trillion. That negative sign is going to flip that fraction. And when you flip that fraction, that negative exponent, you now are going to express it as a positive exponent. And since the numerator is bigger than the denominator, as this number gets really, really large, 3 raised to that power is increasing much faster than 2 to that power. So this value of y, this output of this function, is approaching positive infinity. Alright, so let's think about what happens if we're far away from the origin, but in a positive sense. If we input into this function extremely large numbers, you know, positive 1 billion, positive 1 trillion, and so forth. Well, we've got this base that's smaller than 1, and if you are giving it some positive exponent, and this number is really, really big, you know, huge number, the 3 to that power, this denominator is getting much larger, quicker than that numerator, and this guy is approaching 0. This 2/3 You plug in large positive numbers like that on your calculator, and you're going to get really small numbers. But it's never going to quite equal 0. So this y values, this decimal number is approaching 0. So that's thinking about it in terms of just algebraic, in terms of number sense, in terms of just thinking about what happens when you plug in numbers that are really, really small, or what happens to the output of this function as you plug in numbers that are really, really large. Now, we can also approach this by just looking at the graph. We know some basic things about this graph. We know that if the base is smaller than 1, this exponential function is a decreasing function, that its shape looks like that. We've already seen that the y-intercept is 1. We've already seen that the horizontal asymptote is the line y equals 0, and there is no vertical asymptote. Okay, so if remember this end behavior, we're trying to describe the output of the function. We're trying to describe the y-coordinates, but not over the whole graph, just at the tail ends of the graph when you're very far away from the origin. So if we were to look at points here, and we say, well, as x is becoming negative, as you move to the left, here's 1 point, you move further to the left, the x values are getting smaller. Well, what's happening to stay on the graph? The y values have to be getting bigger, and we know that y is approaching positive infinity. Now down here, as x is approaching positive infinity, as x is getting bigger, you're moving to the right. Now it is true, because this is a decreasing function, that the y values are getting smaller, but they're not getting, over here the y values were getting bigger very quickly. I mean, without bound, they say. The y values are getting smaller, but there's this, think of it as a wall down here, there's this horizontal asymptote that this graph just keeps getting closer and closer and closer to. These y values never dip below that. So these y values are getting closer and closer to 0. Whereas over here, the y values were increasing without any kind of bound. There's no kind of limit. There's not a ceiling. And you can think of this dashed line as a floor. And you can't go below that floor. Alright, so there's the end behavior for problem number 1. Let's take a look at problem number 2. Again, it's an exponential function. Now there's some differences, and some important differences. The base is bigger than 1, and there's 2 transformations. But I don't have to necessarily start thinking about the details if they're going to ask me about the domain, because I can immediately, without any thought, I know the domain of any exponential function is always all real numbers. So on a test or quiz, if it's an exponential function, now other functions, hey, they may not have a domain of all real numbers, but if it's an exponential function, it doesn't matter whether this base like 6 is bigger than 1 or this base like 2/3 is smaller than 1, the domain is going to be all real numbers. Okay, so now when they're asking me about other things about this function, I'm going to have to stop and think. When they're asking me about the range, I know that the range can be affected by transformations. So let's think about what the parent function of this would be, the basic function, and what kind of transformations are happening on it. So this function, its parent function, its basic function, is just 6 raised to the x power. Okay, the -1, that's when you subtract 1 from x, that's a bizarre transformation. It's actually a shift to the right. When you add 3, not to the x value, but to the outside of that, it'll lift it up 3 units. Okay, so let's think about what transformations affect the range. The range is a set of y values, and when you're plotting points, it's the x-coordinate that determines left or right from the origin, and it's the y-coordinate that determines up and down. And y-coordinates are the range, so therefore the transformations on the y-coordinate is going to affect this. So I'm not concerned at all that this -1 shifts the graph to the right 1 unit, because moving to the right is not going to change the domain. But I am concerned about this +3. Alright, So let's come back to this 6 to the x. This 6 to the x, since 6 is bigger than 1, this is an increasing function. Okay, so as x increases, y also increases. Last time when we were looking at this 2/3, since 2/3 was smaller than 1, we saw that as x increased, y decreased, and this was a decreasing function. The base was smaller than 1, it was a decreasing function. Let's make sure that I graphed that, that I didn't make a silly mistake. Yeah, all of my pictures are decreasing functions there. Okay, so, but in this number 2, well, actually I guess it's number 3. I misnumbered it. This 6 is positive. It's an increasing function. It's going like that. So just as before, however, it has a horizontal asymptote at y equals 0. Okay, so what's going to happen with this plus 3? It's going to lift this whole graph up 3 units, including that horizontal asymptote. So if this guy is lifted up 3 units, so take 0 plus 3, well, hey, that's y equals 3. And now it still has that general shape. It's still an increasing function, but it's getting closer and closer to this y equals 3. So the range is entirely above this horizontal line, and that horizontal line is 3. So the range, if you were to describe all of you have a collection of all these points that are on the graph, and you're looking at the y coordinate of every single point, the one thing that they all have in common, they're all strictly bigger than 3. You do not see any point that's on this curve that's below this line y equals 3. Okay. So now an asymptote. Well, we were just talking about that. This horizontal line is the asymptote, and it's the only one that it has. Originally, the 6 to the x had an asymptote of y equals 0. That plus 3 moved that asymptote up 3 units. So there is no vertical asymptote. There is not a vertical line that the graph is getting closer and closer without touching. If you draw a vertical line over here, to properly draw this graph, it's crossing that line, and this guy's moving and it's crossing this. So there is no vertical asymptote. And the horizontal asymptote it wants, remember, an equation is y equals, well, 0 plus 3. Without that plus 3 it's 0, and if you add 3, y equals 3. So the horizontal asymptote for this exponential function is the line y equals 3. Alright, the x-intercept. Doesn't matter that we're studying exponential functions, any function at all that you want to study, to find the x-intercept, you let y equal 0. And remember, our function notation is just a new way that they decided to write the y value. Okay, so to find the x-intercept, where does this cross the axis? Again, I can think about this and do it algebraically, or I can think about what the picture looks like and try to answer it from there. Algebraically, to find the x-intercept, you let y equal 0. So the left-hand side of this equation is 0. We have one equation and one unknown. We can try to solve this equation for x. We subtract 3 from both sides. The resulting equation will have the same solution set as the original, but we've got a problem here. We know that exponents, a negative exponent, never makes my answer negative. This is impossible. We knew that 6 to the x minus 1 had a range that was 0 to infinity. There's no output. There's no way that this is ever going to be a negative number. So there's no x that satisfies this equation right here. There is no solution to this. And if there's no x that has a corresponding y value of 0, there is no x-intercept. This graph, let's think about what the graph looks like. Remember, it had been lifted up. Where did it go? It had been lifted up 3 units. So it's this one that's in this pinkish red. So if I make a quick sketch, I have my y-axis, I have my x-axis, I have a horizontal asymptote at y equals 3, and my graph, since this base 6 is bigger than 1, this is an increasing function, and you can see this graph is entirely above the line y equals 3. There's no way this graph comes down and crosses the x-axis, so there is no x-intercept. We can look at the picture in the graph, or we can conclude the same conclusion algebraically. The y-intercept. For any function, to find the y-intercept, you let x be 0. If x is 0, you haven't moved left or right from the origin, and you're only moving up or down, so you're definitely somewhere on the y-axis. If we just replace this function notation with the y value, we have y is equal to 6. And instead of writing x minus 1, we know that we can replace x with 0, and we've got 0 minus 1. Well, 0 minus 1 is just negative 1, and 6 raised to the negative 1 power will be 6 to the positive 1 power if you move that base down to the denominator. You're adding 3. So 1/6 plus 3 is this mixed number, 3 and 1/6. So my y-intercept is 3 and 1/6. If you were to write the coordinates and plot the point, the zeros telling you from the origin do not move left or right, and this positive value, 3 and 1/6, you would move up, and it crosses the y-axis at 3 and 1/6. Okay. So we're thinking of end behavior. Now again, we can think in terms algebraically, what is the end behavior, or we can think in terms of what we already know about the graph. If we plug in very small values, very negative values into this function, what would happen? Well, the 6, the x minus 1, the minus 1, if x is getting really small, if this is negative 1 trillion, negative 1 trillion and 1 isn't that different than negative 1 trillion. This minus 1 really doesn't have a major effect on the graph when you're far away from the origin. When this x is in comparison to it is significantly different, and the plus 3 is not going to be that much of a change at all either. So we've got this 6 raised to this negative number. That negative number might be negative 1 million, negative 1 billion, negative 1 trillion. To make that a positive value, it's 6 over, that negative will become positive. Hey, this guy is getting really close to 0. So the output of this function, remember, instead of f, we could call this the y value. The output of this function is getting close to 0 as do I have that backwards? No, that's correct. All right, and then as I plug in positive values, then again, let's go back and look at the original. When we plug in positive values, we're talking, that x is approaching positive infinity, really huge numbers. So taking 1 trillion and then subtracting 1 is insignificant. This is still, you may as well call it still a trillion if you get out that far away from the origin. So this minus 1 is having no effect on our value. And then to add 3 is not having any effect either. So if this x is becoming really positive, then 6 to the positive. If this is a really big number, then boy, 6 raised to that number is huge. So this y value is approaching positive infinity. Now that's just thinking in terms of the size of the numbers and number sense, just a theoretical thought process to guess what the y values are either getting close to, or the y values are getting really big. If you want to rely on the picture of the graph, remember that our original 6 to the x was an increasing function, but it had been shifted to the left 1 unit, and then it was shifted up 1 unit. Okay. So I can think of a rough picture looking like this, where my horizontal asymptote is the line y equals 3. So when x is approaching negative numbers, you're far away from the origin on the left. You're looking at that. I often say the tail of the graph. You're looking at this portion of the graph, and we can see there that this is starting to level out, that these y values are approaching, getting closer and closer to 3. Over here on this side, as x is getting really big, you're very far away from the origin. You're out here in this tail area of the graph, and we can see that as you move from point to point, as x increases to stay on the graph, the y values are also going to have to increase. And if a graph, this guy, now there are some functions that have more than one horizontal asymptote, but for these exponential functions, if there is a horizontal asymptote, it only has exactly one horizontal. I shouldn't say if if it's an exponential function, it has a horizontal asymptote and it has exactly one. There's not another horizontal asymptote here, so this guy is y is approaching positive infinity. All right, so let's move on. Now, with this logarithm, I'm going to stop this video and do this in parts, because I tried to make videos before and there was an error and it wouldn't save what I was doing, and it could be because of the size of the video. So I'm stopping here and continuing on another video.